So it's a pleasure to be here and talk a little bit about my trajectory in this area called robot science, which is not just about science of building robots, but it's about making robots that are scientists, robots that can do research. And it sounds a bit strange, but we didn't set out to create this. It's sort of a little bit of a serendipity. So I know there's a lot of students in the audience, perhaps PhD students, perhaps postdocs, perhaps undergraduates. People listen to this talk later. And so part of what I want to do today is not just talk about research results, but talk a little bit about the trajectory of research, how we started going in one direction. I started as a postdoc doing certain things out of graduate school. And then research took me in certain directions. Some of these directions are not things I anticipated in advance, but sort of opportunities. Some things worked, some things didn't work, some surprises, and we ended up after many years creating what we call robot science, robot scientist. So let me take you through that trajectory a little bit so you can see so how things sort of unfold in surprising ways. So my research actually started thinking about how to make better robots. So I'm a roboticist at heart. I try to build robots that do interesting things. And today we are at a place where robots can do a lot of things better than humans. They're very fast, they're very accurate, they're very precise, they can work 24/7. Robots are really, really good at doing certain things, but they have this one main weakness, and that is that robots have a hard time adapting to new situations. In contrast, we humans and animals in general are not as fast, not as precise. We can't do things 24/7. We're not as powerful, perhaps, as these big robots, but we are very adaptive. We can learn to do new things. We can respond to new situations. So I would say one of the biggest research challenges in robotics today is how do you make machines that are adaptive? How do you make robots that can adapt to new situation? So that was the where I started my career. Out of finished my PhD, started my postdoc at Brandeis University, which is in Boston, in the U.S. This is what I worked at the. I got a new postdoc position at the Center for Complex Systems in at Brandeis University. This is what it looks like on a good day. And my research question was, how can I use evolution to breed robots? So the idea was, instead of sitting at a desk and designing robots, which is what most roboticists do, we design robots, we program robots, we build robots using top-down intelligence. How about we breed robots? Just like you breed corn or you breed cows, we're going to breed robots by having lots and lots of robots interact with each other. And we use evolutionary processes to make better robots. So to do that, we built this big, this is work done with Jordan Pollack at Brandeis. We built this big robot simulator. This is back at 2000. So you couldn't just download a physics simulator. We had to build our own physics simulator. In that physics simulator, we allowed robots to evolve by adding robot parts, bars and joints and neurons as the neural networks to control the robots. We allow robots to sort of mutate and evolve with the goal of making robots that can crawl on an infinite plane. So the idea was that these neurons and robot parts will connect to each other, and over time, we'll get interesting robots. So we built this simulator, we built the evolutionary process, and then we put that entire thing on the biggest computer we could find back then. This is again year 2000. We had this big computer in the basement called an Onyx. I don't know if anybody of you have heard about this, the Silicon Graphics machine. It's one of the biggest machine back in 2000. It had 16 processors. Now your cell phone is faster than this computer, but back then it was the biggest computer we could find. And then we hit enter and we let the robots evolve. So what you're seeing here is the chart plotting progress, the speed of the robot over many, many generations. So every dot here is a robot. And you can see that in the beginning, nothing happened in the first 100 generations. Again, generations move slowly. So after about a day of running this on this massive parallel computer, nothing happened. So basically, we're getting a lot of piles of junk with robot parts and neurons and joints and actuators all combined together, but nothing is moving. Nothing is going anywhere. No robots are making any progress. This is about 100 generations into the process, and I was almost ready to give up on this research when suddenly things started to move. Suddenly, around generation 120 or so, you can see there, things begin to move. Now, they don't move very fast. So if you look inside, you see that there are a lot of piles of junk that are, most of them are not moving, but some of them are vibrating a little bit. And these vibrating piles of junk are not moving fast, but they're moving infinitely better than the other piles of junk that are not moving at all. And so these vibrating piles of junk begin to take over the population, and then better ones appear and better ones and so on. And if you let this thing brew for about a week, which is what it took, we started getting machines that learn how to move forward. So here I'm showing you two of these machines that are learned to move forward. They're crawling across the infinite plane. And to me, they're beautiful because, for example, they're symmetric. And we didn't reward for symmetry at all. Nevertheless, symmetric machines appeared, probably because that allowed them to move faster in one direction. And again, there's a neural network, there's the body and the brain is co-evolving here, and you get these interesting machines. So this was a kind of interesting results. Both of these machines evolved on different computers. So I was actually doing a postdoc at MIT at the same time as I was doing postdoc at Brandeis in parallel. And the machine on the left evolved at MIT, and the machine on the right evolved at Brandeis. And I remember the moment they appeared. Very exciting. But I wanted to take this one step forward and build these robots in reality. So another nascent technology back in 2000 was 3D printing. So 3D printers were new at the time. They're very expensive, but we bought a big 3D printer that cost $100,000. It was the Stratasys XS, Stratasys Genesis, with the first machine that Stratasys put on the market. Of course, today you buy a 3D printer for $100, but back then it cost $100,000. And we printed some of these robots, and here they are crawling across the floor of the lab. So again, these are, I think, the first ever 3D printed robots, but they're not just 3D printed robots, they were designed and printed, designed and manufactured almost automatically. And when you look at these robots, they're not great robots, they're not going to take over the world, they're not very fast or very robust, but they were completely a product of this evolutionary process. So that was back in 2000. If you fast forward another 10 years or 15 years today, we can, of course, with faster, better computers, we can make robots that are not just made of rigid components, robots made of soft material, which are much harder to simulate. So here's the example: when we evolve robots made of hard and soft material, you can get much more organic looking robots. These are robots that have soft material in them. They're many more degrees of freedom, much harder to simulate. They require GPU and all that, but you can still get very kind of interesting kinds of robots. So if you fast forward another decade or two, this is where we're at. One of the challenges we have found with evolving these soft robots is, how do we actually build them? The rigid robots are easy to build because we have rigid actuators, but finding soft actuators is actually very difficult. And so we spent some time developing kind of soft materials, soft actuators that allow us to implement these robots in reality. And that's an ongoing line of research. But going back to our story, back in 2000, I sort of we're able to evolve these simple machines that sort of crawled out of the virtual world into the physical world. And interestingly, these machines made it to the front page of New York Times. And I have to say, I was never able to repeat that again. Never got a paper, any kind of scientific results on the front page of New York Times. But back in 2000, the editor of New York Times told me there was nothing else happening in the world in August 2000. Of course, that was going to change very soon after, but there was nothing happening, and they had nothing else to talk about except these robots. And the theme was robots are going to take over the world. We can know how to breed robots. Robots can make other robots. It's the end of the world. So there's a lot of media attention, and that media attention is what got me my faculty position at Cornell University. So despite whatever you hear, media is good. It helps you get positions. And I got my faculty position at Cornell University, which on a good day looks like this, upstate New York in Ithaca. It's a beautiful area called the Finger Lakes, kind of like the Alps of New York. And it's a beautiful area. And I started my faculty position there. And I wanted to take this one step further. I said, okay, evolving plastic robots is good for a postdoc, but for a mechanical engineering career, I need titanium robots. I need serious robots that are going to be difficult to make and to control and can do interesting things. So we built this new robot over here. We called it Nonaped. It has 9 legs. It can roll and jump. It has a paintball canister in the center. It has pneumatic cylinders. It's a very, very powerful robot. It can jump and do backflips and do interesting things. The question is, can we control the valves to make this robot gallop in the field? So that was the challenge that I wanted to address. And I thought, if I can do this, I can get tenure in my department, because this is very, very difficult to do using conventional control methods. So we put this big robot into a big cage. There was a camera at the top left that tracks the red ball of this robot. You can see what it looks like at the top right. It tracks the red ball, and it can measure how fast the robot is moving forward. And then we had lots of controllers, neural network controllers, that were taking turns riding this robot, measuring things and opening and closing valves. And the question is, can we breed a controller that will make this robot gallop in the field? So we put this in a cage. We let it do lots and lots of trials overnight. There was this reel that pulled back the robot at the end of every trial. We leave this overnight, and at the end of the day, we get some interesting robots. I don't know if you can hear the audio, but really it's a robot that, it's playing back some behaviors. You can see in the beginning, it's not moving very fast, but it's kind of learning how to walk over time. It's playing back different behaviors. And you can see here that it's learning how to walk, but it's not galloping. It's not running very fast. It's not going to take over the world again. This robot it's learning to move, but it's nowhere close to the kind of behavior I was hoping to get. So that was a little bit of a disappointment. After spending about 3 years really on this project, we realized we're doing something wrong. So let me take you back. Let's take a look at the 2 projects I just showed you. The first project involved building things in simulation, then breeding things in simulation, building it, and then trying them in reality. And it kind of worked in reality, but only because the robots were very, very simple. So in general, we have this problem called crossing the simulation reality gap. You can do amazing things in simulation, but they don't necessarily carry over to reality, because it depends. Because the more complex the dynamics, the harder it is to carry them over to reality. The second project involved adaptation in reality. We evolved everything on the physical robot. There was no simulation, but the challenge there is that it took too many physical trials. There's only limited number of things you can do in physical trials overnight. Maybe you can do 100, 200, 1,000 trials overnight. It's not enough to train a system to do things in reality. And so the robots were not able to learn. So what do? We can't do things in simulation, and we cannot do things in reality. So what do? So the third project I'm going to show you is a project where we said, okay, we're going to do something hybrid. We're going to start by breeding robots in simulation, but I'm putting a simulator in quotes because it's going to be a bad simulator, a simulator that's not very accurate. We're going to evolve robots. We're going to try them in reality. The robots are not going to work very well in the first time because the simulator is not good. But then we're going to collect data from the robot, actuation and sensation, what the robot did and what it felt, accelerations and so on. We're going to use all that data to breed better simulators. Just like we were breeding robots in a fixed simulator, now we're going to breed simulators that are going to compete over whether they can simulate the robot. Who can best simulate the robot? And we're going to base them on data that we could collect from the robot. All right, so in the first project, we bred robots. Now we're going to breed simulators. In fact, we're going to do it all at the same time. We're going to what's called co-evolve, co-adapt two things at the same time, robots and simulators. And hopefully together, they are going to adapt each other. So sometimes this is called adversarial learning. Today, this is a big field called adversarial learning, where we have two things adapting or learning at the same time, and they challenge each other. The robots need to evolve inside simulators. The simulators need to match up the experience of the real robots, and they adapt to each other at the same time. So let me show you how that project works. So this is my third robot. This is a four-legged machine that needs to learn how to walk. But the challenge is that this robot does not know what it looks like. All it knows is that it has, so this robot that it has 8 motors, 2 on each leg. But again, the robot doesn't know that it has 4 legs. It just knows that it has 8 motors. And it has 2 tilt sensors that tell it how it's tilted left and right. But the robot doesn't know if it's a snake, a spider, a tree, a robotic arm. It doesn't know anything about what it looks like. All that it knows, it has 8 motors and it has 2 tilt sensors. So to understand what that means, imagine yourself for a moment sitting in a black box on a chair, inside a black box, no windows. All you can see in front of you are 8 knobs. And as you turn these 8 knobs, the box tilts left and right, forward and backwards. And you can feel it tilting. And you need to get that box to move forward. But there's no windows and you don't know what you're sitting in. So this is what this robot feels. Maybe it's not unlike what a brain of a newborn child feels, but it has access to all these actuation muscles, and it needs to learn how to move forward or to do things. Here's how this robot works. It begins by moving randomly, and then it begins to hypothesize about what creates hypotheses about what it might be. Is it a tree, a spider, a snake, a arm? It creates all these hypotheses, all these stick figures that I'm showing in the top left that match up with the data. These are simulators of itself. And then in the green box on the top right, it does the next step where it tries to figure out how to actuate the motors to create the most disagreement between predictions of these models. So if it doesn't know if it's a snake or a spider, it can move motor 8, and if it's a spider, it should tilt left, but if it's a snake, it should tilt right. So it's looking for how to actuate the motors to create disagreement between the predictions of the models. So this is a little bit like, and I hope you see the connection to a robot scientist. It's trying to create, it's like a scientist that designs an experiment to create the most disagreement between predictions of 2 competing theories. Because then the results from the experiment will refute at least one of the theories. So it looks for what actions to create this variance in predictions of the models. It then does those actions, creates more data, eliminates some of the models, looks for more disagreement, does the experiment, collects more data, eliminates more models, and so on. It goes in a cycle until all the models converge. Once they converge, it can figure out how to use that model to make the model walk and on the bottom right. And this is called behavior synthesis. And because the model is indistinguishable from reality at that point, what makes the model move forward also makes the robot move forward. So that's the basic idea. And we tried it by, here's the robot in its first experiment, trying to create a model of itself. And here it is trying to move in physical reality. It is sort of crawling around and unplugged itself. So we plugged it back in and tamed it down a little bit. And here it is moving forward again. It's now it's a period of about 4 days where it's breeding these internal models. You can see at the beginning, it doesn't have no idea what it looks like, if it's a snake or a spider and how pieces are connected. This is about 2 days into the process. It's pretty much figured out that it has 4 legs, doesn't quite know how they're connected. And this is 4 days into the process. It pretty much figured out what it looks like and how it's connected, and it doesn't get it exactly right, but it's good enough that it can then use that self model to figure out how to walk. It's not learning how to walk in reality, it's learning how to walk inside its self simulation. And here it is walking in reality for the first time. So again, we were hoping to get an evil spidery walk, but instead we get this kind of strange way of moving forward. But when you look at this, you have to remember the robot did not do trials of walking before this. It did not learn in physical reality. It was not programmed with rules. It just created a model of itself and then it figured out how to walk. So to test it, we did something very cruel. We plucked off a leg and we watched what happened. And the robot doesn't immediately notice that a leg comes off, but it does notice that its dynamics, its accelerations are different than what its self-model predicts. And it goes back into the cycle of self-modeling, and within about a day, it also loses a leg. And you can see here that the leg became the pink leg is a lot shorter. And then here it is walking in reality without the legs. It learned how to move forward without the leg. And again, you have to remember there was no sensor that said leg came off, switch to plan B. It's all the dynamics change and therefore the self-model change and therefore the behavior change. So again, it's all about adaptation. So remember, I started this talk talking about how adaptation is the big challenge in robotics. And what you're seeing here is a robot that is adapting to a very different situation where one of its legs came off. And it's adapting not because some programmer programmed it to behave in a different way, but because the dynamics changed, therefore the self-model changed, therefore the behavior changed. And to show you how this works many times, the origin there is where the robot begins. These are 13 independent runs. You can see that when you have no control, a random controller, you get the red behavior. Then it's at the red location. But when you get when the black dots show you where the robot believes it's going to be, get using its self model, and the blue dots show you where the robot actually arrives. So what it shows you that, like anything else in academia, this robot has an inflated self-image. It believes that it can go twice as far as it really can, like all of us. But nevertheless, as this is really interesting from a psychology point of view, this inflated self-image allows the robot still to make the right kind of decisions about how to learn how to walk. And this is kind of very interesting to me because we as engineers always try to create accurate simulations. But what you see is that when the robot simulates itself, it doesn't make an accurate simulation. It just makes a simulation that allows it to make the right kind of interesting, tells us something about sort of what is the best kind of simulator. So that was 2006. If you fast forward to 2019, today with deep learning, we can create much more complex models from scratch. So here the robot doesn't know anything, but you can see in the beginning has no clue what it looks like. This is deep learning. It doesn't even know about Newtonian mechanics. But after about a day of training, its self-model is accurate enough that it can do all kinds of things, all kinds of planning using the self-model. You can see the self-model in the background as a phantom compared to the real robot, and you can see it's pretty close to reality, close enough that the robot can learn how to do interesting things. And again, we changed the robot by replacing one of its parts, and here the robot in about an hour creates an adaptive self-model, and once its self-model is adapted, it can continue doing its task as if nothing has happened. So that was 2019. Right now, we have a paper that is almost published in Science Robotics. It is conditionally accepted, where we have a new kind of architecture that allows the robot to model itself using sort of model its shape in a completely unstructured way, and you can see how what that model actually looks like. It's getting very close to reality. So here's how the robot sees itself, again, based on all kinds of, it's a sort of shape kinematics that it's learned over time. So this is where this kind of whole line of self-modeling is. And of course, a lot of our research now is focused on robots, not just the robots that model themselves, but robots that can model other robots, very much like theory of mind. So we humans, we see each other and we have thoughts about not just what we look like, but what other agents, what other people do and think, and what other agents plans, and we can experiment with these things with robotics as well. And I won't talk much about that except to say that you have here we have robots that are playing hide and seek. In order to play hide and seek, robots need to understand how other robots see the world, and how other robots, what other robots can do, and what other robots plans are, and so on. So lots of interesting explorations there. But going back to my story, it's 2006, and we have these robots that learn to model themselves. And now the big question, another student comes into the lab and says, wait a minute, how about we apply this to other kinds of problems? In fact, a robot that models itself is simply it's modeling a black box dynamical systems. What if we take a system with lots of inputs and lots of observational outputs, and we try to model the dynamics? We can apply this to any system we want, not just to robotics. So here's an example. Let's say I take my robot, and instead of that robot, I change it to any arbitrary experimental system that has inputs and outputs, has initial conditions, and has output sensors. Any experimental system. Instead of modeling the robot out of robot parts, I model it out of mathematical parts, like differential equations with plus and minus and multiply and divide and logs and exponents. And instead of changing the action of the robot's motor commands, I change the initial conditions of the experiment. So basically, I've taken the same system I've shown you before, with a robot that does arbitrary movements and create models of itself, to an arbitrary experimental system where I can change the initial conditions and create models out of mathematical building blocks, and I change the initial conditions to make these models disagree. And how does that work? So now, instead of the robot doing experiments, I have a human collecting data to feed the models, or it can be another robot collecting data to feed the models, or even a database that where a lot of experiments are collected. So we can apply this to lots of different things. I'll show you some quick examples. Here's an example of a footbridge. This was at Cornell University. I was at Cornell at the time still. And when you cross this bridge into Cornell, when you walk, this bridge wobbles. And I was always wondering what happens if one of these parts of the bridge are not as strong as they need to be. So we can do the same kind of approach where we vibrate parts of the bridge, and we create lots of models of the bridge that meet those vibrations, and then we measure, you know, how to vibrate the bridge again to create disagreement between predictions of these models. And then we vibrate the bridge again, collect more data, improve the models, find out how to make the models disagree in their predictions, and so on, do this in a cycle. And we could show that we could find the weakest point in the bridge a lot faster and more accurately than conventional civil engineering approaches that were used at the time. Here's another example. We have a black box with an electronic circuit in it. We actuate that circuit in lots of different ways. We create models. We find out how to actuate the models again to create disagreement between these predictions. And very quickly, we can recover what is inside that black box. So again, simply by changing the building blocks, the language that you use to describe a system, you can create lots of different models. So I want to focus the remainder of this talk on creating regression models, symbolic regression models. So let me say a couple of words on symbolic regression. So you all know what regression is, right? Linear regression, nonlinear regression, where you have a formula and you want to adapt the coefficients of the formula to best fit data. Symbolic regression is when you have data, but you don't even have a model. You don't know at all how to fit the data. So if, for example, if I showed you this data on the left there and I ask you, what is the mathematical model that best fits this data, you might look at this and you say, well, there's an oscillation and it seems to grow. So maybe it's an exponent times a time. If this was a live event, I'd ask you to make this kind of prediction. But if you're trying to do this in your head, you're trying to do this symbolically. You take all these basic building blocks that you're familiar with, exponents and trigonometric functions, and you try to put them together to make a function that fits this data. And I could give you a different data set like this one and ask you, what is the function that generated this data? And this will be a really, really hard question, right? Okay, maybe there's a sine wave, maybe not, or what is it? So this is called symbolic regression. And arguably we do this as scientists all the time. So the idea was, okay, we can just like we breed robots and breed other things, we're going to breed mathematical expressions to fit the data. So we represent expressions as trees, and we evolve expressions to minimize the error until we find an expression that best fits the data. So this is called symbolic regression. It's an idea proposed by John Koza in 1992, but there's only one problem, that it tends to get stuck on local optima. It takes a lot of computing power. It doesn't really work well back in 92. So what we did is basically made only one change to this very basic process. Instead of fitting the models to the entire data set, we are going to co-evolve. Remember, we are all talking about co-adaptation, co-evolution, adversarial learning. We're going to co-evolve the data points that cause the most disagreement in the models, right? So we fit models to subsets of the data, and we co-evolve subsets of the data such that they cause disagreement in predictions of models. So data points that all the models agree on their prediction are not useful for ranking models, but data points that cause disagreement are good for ranking models. And so we co-evolve models and subsets of the data, and now we can see that we can create this model a lot faster. Here's this data set that I just showed you. You can see the red dots jumping around to where the disagreement is maximum between competing models, and very quickly it can find out that it was an exponent times a sine wave. And in fact, if we run this many, many times, we find this interesting result that if you use the entire data set, you kind of improve with time. But if you use co-evolved data sets, subsets of the data that are co-evolved to maximize disagreement, you can find the correct model faster and more accurately than using the entire data set. And this is very, very surprising. Most people feel that if you use the entire data set, you always get the best results. Why not use all of your data, right? This is our intuition. But what we found here is that actually, if you're using your entire data set, you're not going to get the best results because your data set is probably biased. It has a lot of data in some parts and not enough data in others. But if you use co-evolved portions of the data set, you get to focus on the right places that you need, and therefore you can find solutions a lot faster and sooner than using the entire data set. In fact, we also found that for the same amount of computational time, if you use the entire data set, you get complex, large solutions. And if you use co-evolved data sets, you get simpler solutions with the same accuracy. Okay, so we found this great thing. What do we do with it? So we try to do all kinds of things. Of course, we try to predict the stock market. Like anybody who has an incredible tool for predicting things, we try to predict the stock market. We were not successful in that, so this is why I'm still here. And we try to do other things. So we threw in other things. We said, okay, let's try to find a formula for the prime numbers. Let's see if we can do that. So we tried that. Obviously, we weren't successful for that either, although we did find some interesting solutions, approximations. So seeing that we're not going to be rich or famous, we said, okay, let's write some papers and see what we can get. So we wrote some papers, and then I got an email from a group at CERN in Switzerland, or actually in France, who said, hey, we have this big data set of binding energy gap of atomic nuclei. I don't know exactly what this means, but it was very important for them. And they said, maybe you can find a formula that explained this gap. So we took the data set, we ran it a day, and we found this beautiful equation that explains the gap to 3 digits. So we were very excited, and I emailed the guy back, and he emailed me back immediately and said, we were very proud about this. And he emailed me back and he said, we actually already know about this formula. It's called the Weizsäcker's formula, and our formula is correct to 4 digits. So he was disappointed, but actually we were very proud because we said, wait a minute, we can find named formulas that people got Nobel Prizes for. So maybe we can find a new formula for some other problem and we will be famous. And so we said, okay, let's take it up a notch, and we're going to model dynamical systems. Instead of just fitting equations to data, we take time series data, we compute the derivatives, and then we fit the derivatives, and that gives us differential equations. So we can model dynamical systems, kick it up a notch. So to test it, we took this 7 differential equation system that describes the glycolysis cycle in the cell. Frankly, I don't know what that means either, but we just thought these are cool equations. We generated data and we fitted them and we ran our algorithm, and it could find from the data with noise the 7 differential equations from scratch, just looking at that noise. Again, we are very proud of this. We wrote a paper and we said, we have this tool. It finds differential equations from data. Let's see what we can do with it. To test this, again, we tested it on our own research. As Julia mentioned in the beginning, we do a lot of work on 3D printing as well. And so on the side, we had a project where we were 3D printing these mosquito things that clap their wings and fly in the air. And there was a big problem there. We're trying to calculate the lift from an aeroelastic wing. This is a really, really hard problem. And we said, okay, we can collect all the data and see if we can create a model for the lift. And let's see if we can try our own thing on a real problem. And I want to show you the result that we got, but I won't show you the formula. I want instead to compare it on the scale of lots of different equations. So in general, when you talk about science, this is true for all of science, not just robotics or air elastic behavior. You can compare models on 2 axes, accuracy and complexity. This is true for all scientific theories. Some theories are simple, but not very accurate. F equal ma. It's very good, very simple, not perfectly accurate, but it's good enough and it's very, very useful. Some models are accurate, but complex. And we sometimes need very accurate models. And even though they're very complex, they're very, very valuable. And there's a lot of space in between those. Lots of PhDs in between these things. Now, occasionally you find a model that's simple and accurate, equal MC squared. This is where you get a Nobel Prize. This is the best thing to be in this corner. But unfortunately, most of us end up here in this corner where we have models that are complicated and inaccurate. But this is all of science, is all here. So where do the models for these air elastic behaviors, where do they end up? So here are lots of models from papers published on air elastic behavior. Every dot here is somebody's career, all right? And the models created by our systems are all here. And what's important about these is these models are simpler and more accurate than models created by human scientists. Now, Occam's razor says if something is simpler and more accurate, it is closer to the truth. We don't know what the truth is, but that's a good axiom to go for. And here's the performance of lots of different polynomial models. So we have this tool. Another example, another student walks into the lab and says, I want to model the interaction between tires and roads. Now you might say, wow, that's interesting. Why do you want to do that? Maybe for improving road tire safety, maybe for improving vehicle performance and efficiency. So he said, no, I want to do this because I want to improve video games. All right. Different people have different motivations, but he got this huge data set. And again, he could find models that are simpler and more accurate. That's a red dot compared to state-of-the-art models for road tire interaction. So at that point, I was walking around the world, giving colloquiums, traveling all over the place, giving colloquiums, begging for data. I said, I have this system, I have this hammer, I'm looking for nails. If you can give me data, we can find equations and write a paper, and maybe we can make some discoveries. And most people don't want to share data, I have to tell you. But this one scientist, Girl Sewell, was now in UC San Diego, said, I have this perfect data set for you. I'm measuring different things for different cells, different markers going up and down for different cells, and maybe you can create a model that matches these dynamics for all the cells. So we took this data set, we ran it on our system for about a week, and we got these two equations at the top there. So I'm showing this, I showed this data set to Gurul, and he emails me back and says, it's total rubbish. This doesn't explain anything biological, it's totally wrong. And we were very disappointed. But we knew we're doing something wrong. And we thought about this for a long time, and we realized we're probably giving it the wrong building blocks. We give it sine and cosine are irrelevant to biology, but we're missing something else. And we realized we're missing time delays. So in biology, you need time delays because there's diffusion and things don't happen exactly the same time. It's not like a pendulum. Biology has time delays. So we threw in time delays into the system. We hit enter again, and bam, we got these two beautiful equations that explain the entire data set. And emailed me and said, look, we have a problem because these two equations are simpler and more accurate than my models that I published in Science, he said. And so we have models that are simpler and more accurate, but there's only one catch. We don't know what they mean. Whereas models that Gurul published earlier, he can justify every parameter. The models that our system generates are opaque. They're like copying the result from some student, copying your homework where you have the results, but you can't explain how you got it. And this is exactly the situation we're at. Our models are simpler, they're more accurate, they even work for new cell lines that were not available at the time we did the original experiments, and yet we cannot explain how they mean. So that brings me to the end of the talk, which is the search for meaning. And I don't mean that this kind of search for meaning. I mean really scientific meaning, understanding why things happen the way they do. And so this is a little bit different than simple correlations, but where we talk about how things move around and what is correlated. Like, for example, people found that if you sell diapers on Thursday evenings, people who buy diapers on Thursday evening also buy beer. This is a well-known correlation. If you're a business owner, you don't care, you just move the beer next to the diapers and that's it. But if you're a scientist, you want to know why things are happening. And so I want to give you this last example where we said, okay, we're going to find how things work by looking for invariants. And again, the example here is if I show you angle and angular velocity and I ask you of a pendulum, ask you what is not changing about them, the answer is, if you think about this, not the ratio or the sum, It's the formula, it's the total energy of the pendulum that is not changing. So invariance gives us insight. So we took data from a double pendulum and we put it in and we asked, what is not changing about the data? What is the formula that takes in this entire data set and is not changing, is constant across the entire data set? So we put in all the data, we hit enter, we waited for a week, and finally we get the formula that is constant across the entire data set, and that is a constant. Of course, it wasn't really 42. We just got a formula that was a constant, just a number, because a fixed constant is constant across the entire data set. The evolution quickly find out that the formula that's just a number isn't changing across the entire data set. So we penalized it and made it, we forced the formula to use the variables, and it said, it came back with this number. And so on, we keep on going, and it was not able to find a formula that is constant across the entire data set. So I ended up giving this as homework assignment. I said in one of my courses, I give you a data set, find the equation that is constant for all these data points, that you put in the X and the Y, and it gives you the correct answer. And one of the students, Michael Schmidt, came back and said, I know how to do this. You have to reward the evolution in a particular way. He said, you look at partial derivatives of relative variables, dx, dy, dx, you compare them. It's a long story. There's papers around this. But if you do this, it works for lots of different systems. And he showed, we did this experiment here first with a simple oscillator, and we asked what doesn't change. And we got here this, we collect this with a webcam, and the system and says, these are the invariants of the system. And it turns out this is the Hamiltonian and Lagrangian of an oscillator. We kicked it up with a pendulum. We asked what is not changing. It quickly comes back about an hour with Hamiltonian and Lagrangian of a pendulum. Here's a double oscillator. What is not changing about this? Well, here's the Hamiltonian of a double oscillator. This is already stuff that's pretty hard for most people to do. And of course, we took the double pendulum again. We collected data from it by watching it in the dark with a LED, create these beautiful patterns. But here's the data. We said, what is not changing over it? It took the system about a day to search for invariance in the double pendulum. And after doing that, it was able to find the Hamiltonian of a double pendulum, which is really hard. And if we go back, we applied it to our cells, we were similarly able to find the invariance of these cells, which turned out to be really interesting, has to do with the competency level of the cells. All right, so to summarize, we were able to find invariance in both mechanical and biological systems. But one thing always bothered me is, how did we know to even look at the variables of angular and angular velocity? And the question is, is there a way to find these variables automatically? And that's what we're working on right now. And we have a big neural and deep learning system. This is work that's still unpublished, that's looking at videos and making predictions. And from those predictions, it's able to extract what the actual variables are. So this is work that's ongoing right now, and it is in review, and is able to find the actual variables. So, we know that we can't evolve Shakespeare, but the fact that we can evolve science is really interesting. The New York Times wrote about this work. Theoretical physicists are not yet obsolete, but scientists have taken steps towards replacing themselves. And it was very hopefully clear that we are not being replaced. We still are needed both to collect the data, but more importantly, to assign meaning to the results. And I'll leave you with that thought. Thank you.